Hello and welcome back to our series on abstract algebra. In the last video, we took a look at some finite rings and saw how they could be used to solve the problem of closure and closure under addition and multiplication. And to do it, we kind of set up this weird arithmetic structure, right, where 1 plus 2 could equal 0 in Z3 here, for example. And the caveat here, remember, is that these are not actually numbers the way that we ordinarily think of them. These objects here are actually congruence classes. Okay, so the purpose of the next few videos will be to go over these objects in more detail so that we can see exactly what they are and how they behave. And so that we can prove that these structures I was talking about before are actually rings, the way we've defined them. So without further ado, we'll start in this video with the subject of congruence itself. Okay, so we'll look at its definition, some examples, and we'll establish some important properties of congruence that will be useful later. So first of all, let's look at the definition. If we have a, b, and n, all integers, okay, with n greater than 0. So n has to be a positive integer, but a and b can be any old integer. We say that a is congruent to b modulo n if n divides a minus b. Okay, another way you could think of this, right, a minus b is divisible by n. That means we could write a minus b is equal to n times k, where k is some integer, right? A minus b is a multiple of n here. If that's the case, we say that a is congruent to b mod n, right? So this sort of triple equal sign means congruent. All right, now this definition is a bit strange at first, and it can take some time to get used to it. So let's just go through a few examples. So let's start off with this one. We could say 17 is congruent, I'll set over here actually. 17 is congruent to 9 mod 4, okay? Because 17 minus 9 is equal to 8, and 8 is equal to 4 times 2. Right, so you see in this example, our n here is 4, okay? And our a and b are 17 and 9. Right, so 17 minus 9 is equal to 8. 8 is equal to 4 times 2. Right, 4 is divisible by 8. So therefore, 17 is congruent to 9 modulo 4. Okay, another example. 43 is congruent to 8 mod 7. Okay, because 43 minus 8 is equal to 35, which is equal to 7 times 5. So again, 7 divides 35, which is 43 minus 8. So therefore, 43 is congruent to 8 mod 7. As a third example, 14 is congruent to 2 modulo 3, because 14 minus 2 equals 12, all right, which is equal to 3 times 4. So that's what the definition means. Now, it's worth it to take some time to establish some important attributes of this relationship that we've called congruence. And to do that, we're just going to take a look back at high school algebra and the normal relationship that we're used to dealing with called equality, right? So with equality, we have a few fundamental principles, right? One is that every number is equal to itself. This is called reflexivity, right? The reflexive property. We have if A equals B, this implies that B equals A, right? In other words, it doesn't matter which side of the equal sign the numbers are on, it means the same thing. This is called symmetry, okay? And then the last one is called transitivity. Here we have if A equals B and B equals C, then this implies that A is equal to C. Okay, that's transitivity. Nothing revolutionary there, all stuff that you've probably seen before. Now, the remarkable thing is that all of these properties hold with our congruence relationship. Okay, so first of all, let's look at the first one, reflexivity. Every integer is congruent to itself mod n, and it doesn't matter what n you're talking about here either. Right, to see this, just note that a minus a is equal to 0, and 0 is divisible by n. 0 is divisible by every integer except itself, right? We could even write this as n times 0, so it fits our definition. Okay, so every integer is congruent to itself. Now, what if we have a congruent to b mod n? Right? Does that imply that b is congruent to a mod n? And the answer is yes, and this is actually pretty easy to prove. A congruent to b mod n means a minus b equals n times some integer, let's just call it k. Right? Now, all I have to do here is just multiply both sides of this equation by -1. And when I do that, I'll get b minus a on the left-hand side equals negative nk, which I can write as n times negative k. Okay. Negative k is still an integer, so the definition still holds. b minus a is divisible by n. Therefore, b is also congruent to a. Okay, so symmetry holds for congruence. If you have one, you have the other by necessity. Now, what about transitivity? Well, if we have a congruent to b mod n and b congruent to c mod n, does this imply that a is congruent to c mod n? And the answer again is yes. Here we have a minus b equals nk, for some integer k. B congruent to c means we can write b minus c is equal to n times some other integer. I'll just call it p, right? So k and p are just two arbitrary integers here. Then what I can do, okay, is I'm going to add these two equations together the same way that you would have done in high school if you were solving a system of equations, right? I'll get a minus b plus b minus c equals nk plus np, okay? The b's cancel out, and I can factor the n out. And since k and p are integers, k plus p is certainly an integer. Therefore, a is congruent to c mod n. So transitivity holds as well. So the fact that these three properties hold will be very important later on. One other property that we want to establish in this video. There's another important idea that you've encountered before in your high school algebra, and that is that if we have a equals b and c equals d, this implies that a plus c is equal to b plus d. Okay, and also ac equals bd. It turns out that the same thing holds for congruence, okay? So if I have a is congruent to b mod n, and c is congruent to d mod n, this implies that A plus C is congruent to B plus D mod n. Okay? And we'll just do a really quick proof here. A congruent to B mod n means that A minus B equals n times some integer k. We can do the same thing for C and D. Okay, so let's say C minus D equals n times some other integer p. Okay, then, just like I did over here for transitivity, I'm just going to add these two equations together, and I will get A plus C minus B minus D equals n times k plus n times p. And then all that's left is to do some fancy schmancy factoring, and we'll get A plus C minus B plus D equals n times k plus p. Okay? Oops, put the parentheses in the wrong spot here. Should go there. There you go. That makes sense, right? So all I did on this side is I factored out the negative sign. I factored out the n here. So now you can see pretty clearly I've got A plus C minus B plus D equals n times k plus p. Therefore, A plus C is congruent to B plus D mod n. Okay, the same thing is also true for their products, right? AC will be congruent to BD mod n. I'm not going to prove that right now, just in the interest of time. You can do that on your own, following a similar template. And that's everything that I wanted to discuss here in this video. These properties that we've established here will be important in the next video when we start talking about proper congruence classes. Okay, so in the next video, we're finally going to start tackling these objects that make up the finite rings that we discussed in the last video. Thank you for watching.